Welcome back to In Depth with Academia. I'm Richard Price, CEO of academia.edu. It's so good to have you here with me again. Today we're going to tackle a topic that, well, it's super foundational, but also a little mind-bending, if I'm honest. We're going to explore a paper by David Lush called Dirac Quantum Theory Using Alternative Relativity. Let's just say it's not for the faint of heart, but I'm going to walk you through it, and my goal is to make it accessible, not overwhelming. As always, I'm just presenting the content of the paper. I'm not endorsing it, so please treat everything here as insight and not gospel. All right, diving in. What's the real heart of this paper? What's the core problem it's trying to address? Lush is basically asking, can we take Dirac's famous quantum theory of the electron, which is, a pretty big deal in physics, and make it work with a lesser-known alternative version of relativity called Osiak relativity? If that question doesn't make your eyebrows go up, maybe I need to say it differently. The paper is poking at whether the most famous equations we have for electrons have to be connected with Einstein's relativity specifically, or if there's wiggle room. Why is this even significant? Well, if you change how relativity works, even in subtle ways, it shakes foundations under all modern physics. That affects things like what antimatter is, how energy gets calculated, and in a big picture way, even our understanding of dark matter or the early universe. If you're someone who likes certainty, this might be a little chilling, but also exciting, right? Because science is about questioning. Let's pause so I can say these alternative theories. I always picture a group of physicists in a smoky cafe somewhere, arguing about whether photons are really what we think they are, or if there's just this one guy in the corner muttering about half-energy photons. I don't know, does anyone even go to smoky cafes anymore? Okay. Straight back to the material. Standard physics says Dirac's equation for the electron predicts things like electron spin and the existence of something called negative energy states, which, no kidding, ended up being real, in the form of positrons, also known as antimatter. Now, the equations of special relativity, as Einstein formulated them, are intertwined with quantum mechanics at this level. Lush's paper takes a different angle and builds off of Osiak's alternative relativity, which, stay with me here, calculates energy differently. It halves the calculated energy for a particle and changes how kinetic energy is computed too. So what does Lush actually do? He tries to see if Dirac's predictions, using this Osiak relativity math, still match what's actually observed. Would the math still explain antimatter? Would conservation laws like energy and momentum conservation still hold up or break down? Here's where things get juicy. Lush finds that mathematically, Dirac's quantum theory is compatible with Osiak relativity if you reinterpret a few crucial things. For example, those negative energy states that in Einstein's view become positrons. In Osiak's system, they'd actually be states with positive energy but negative time direction in form momentum. Antimatter, in this story, becomes matter, literally going backward in time. It's kind of wild, right? And there's a tangible payoff here. One of the arguments is that in this Osiak framework, certain puzzles in physics, like why we don't see more energy in particle collisions or why spin-orbit interactions have the strengths they do, could be better explained. Oddly, Osiak relativity even allows energy to not always be conserved in some collisions at high energies, although momentum is, which is not what we are taught in school. Lush suggests these features might help us interpret dark matter or dark energy differently. What about experimental consequences? The paper claims, and this is where you as a listener might perk up, that it's possible to tell, experimentally, which relativity theory is right. For example, if electrons and positrons created in high-energy collisions display behaviors predicted only by Osiak relativity, that would be a big deal. But let's be clear here. This is all theory at this stage. The experiments would need to be quite precise and probably a bit tricky to pull off. All right, let's tie this up. The point Lush wants folks to take away is that while Einstein's relativity has been unshakable for a century, there's nothing in principle that says Osiak's version can't be right, at least as far as relativistic quantum theory for free electrons goes. But science is always moving, always questioning. This paper is a great example of how academic research lets us step back, challenge assumptions, and hopefully find some new ways forward. So, whether or not you're a physicist or just someone curious about why the world is the way it is, remember, none of this is absolute truth. It's a perspective, a proposal, something to think about, and maybe, down the road, to test. Thanks for joining me for this whirlwind tour through David Lush's paper. Stay curious out there, and remember, academic research is a living, breathing conversation, not the final word. See you next time.